Oh, Christian?
Yeah, sure.
Yes.
Hey, yeah, thanks for the about the homework. Sorry, I don't know. I think I just kind of rushed through it and missed some things. So
That's perfectly fine. Don't worry. Yeah. I guess since I'm not graded, that's pretty reasonable.
okay, I appreciate it.
Today the audio is very high. Typically it is low. Can you speak something, Christian?
Yeah, just testing. Is that okay?
Thanks.
Yep.
Okay. Yeah, Matt and Jeremy. Yeah, give it a minute. Usually Borden is there. Okay, let's proceed. Yeah, Curtis is here and Borden is there. Yeah, okay. So let's do our homework 10. Even though we do find the expression for radiation in an elaborate manner, the example that I do in the homework is just one example that is purposely to keep it simple. But it's a very important homework in the sense that, or it's an important problem in the sense that this is what triggered quantum mechanics altogether. Like remember that if there is an atom, there is an electron moving around the proton, and invariably it has to be accelerating because it's a circular motion. If anything does not go in a straight line, it has to be accelerating. And what we will see is that if a charge accelerates, then it has to radiate, which means you have to emit energy. Like radiation is a kind of energy that you're releasing. And atom will lose its energy, which means that it will be unstable. It will disappear after a while, right? If you lose all the energy, it will disappear. And you will calculate how much is the lifetime of an atom if it were to radiate in the classical sense. And it will come out to be a few seconds. Right? So none of these atoms that you see around should be existing if they really are radiating. So what we are going to derive today will imply immediately that atoms should radiate, but they do not radiate. So that is a contradiction, which is what led to pretty much a hypothesis as far as new science is concerned that this cannot happen, which is quantum mechanics. And you do it using quantum mechanics, but just because there is a mismatch, you had to do that. So that's what your homework. So it's a conceptual part. It's good, but homework itself hopefully should be straightforward. It uses Newtonian physics, and relatively speaking, mathematics should be simple. So we have the final exam. There will be 2 more homeworks. Maybe you could clarify that. So 20, 22, 23, right? So homework 11 will be due April 23rd. This is tentative. I haven't posted it. and homework 12 is expected to be due 30th, oh, not 13th, 23rd, 30th. And we'll have a final exam. It's on May 3rd, Monday. Probably it will be online exam. We'll see how it goes. I'll update you on that as we reach that. Okay, we are talking about radiation. That means to say if charges are moving around freely, at this point we don't specify what exactly is the motion of the charge. In general, we would like to have a charge distribution, and what is the electric field and magnetic field relatively far away. So radiation deals with situations where t minus t prime, let's call this characteristic time, it is very much less than 1 over c times r and l prime. So this is a characteristic time. By characteristic time, we mean some time which is a property of the system we are dealing with. For example, if it is an atom, the time period of the time period of the electron around the atom is a characteristic time. So the time scale in which things happen in that system. And we showed that if you have a charge distribution like this, so if you have positive charges moving around in a complicated manner, right? So that's your system, and your observation point could be very far. In fact, we would extend it all the way and talk about infinite situations, and we will see that actually energy will still be there. Usually in the problems that we have dealt with in statics, electric field goes as 1 over r square, and 1 over r square by the time it reaches, if we were to calculate the flux all the way at infinity, that will be 0 if there are no charges at infinity. But we will see that radiation fields are different. So in a sense, it's a different boundary conditions. So let's, we discussed this potentials associated with these fields, and we said that they satisfy superposition principle in both time and spatial coordinates. So integrate over all space, all time, and the electric potential due to a point charge at r prime at an instant t prime is given by this expression. That's the delta, the numerator, delta function in the numerator is a new feature in here. And that's your r prime, it's t prime. There was a similar expression for the vector potential also. And we could actually do the t prime integral immediately, except that this whole thing will go and sit in there. Right? So this is equal to 1 over 4 pi epsilon naught. Do the t prime integral, and we get the charge density of prime. And now evaluate it at what is called the retarded time, which is t minus 1 over c r minus r prime. in the approximation that we are talking about, it's not really appropriate to say approximation. This is a radiation condition in the sense that under what conditions will there be non-zero fields available at infinity, right? So in that way of posing the problem, it's not really an approximation. It's actually the construction of the problem itself leads to that. So in radiation, what we have is that r minus r prime is large, and we could call it the far field approximation. We said that r minus r prime is nothing but the position r itself minus of r hat with r prime. So that was an approximation. So that's a far field approximation. Oh, I think this is getting this not in the. So this is, now this is an approximation. But that's the approximation that leads to the leading order to the radiation. And we also said that as far as denominator is concerned, we don't need to keep all of them, so it's just 1 over r. So if we substitute that in there, our expression becomes 1 over 4 pi epsilon 1 over r, and this is dq bar prime charge density, not evaluated at time t, instead it is evaluated at minus r over c. So that's a minus, so this becomes a plus r hat, and it's dotted with r prime over c. So that's your expression. Right away, one should point out that if we were doing statics, the electric potential would be just 1 over r. And if things were at the origin, right? So if you had, what we are doing is that there is a small region, as when you look at it from very far away regions. So that's your r. And somewhere here is your charge, but in the extreme situation, this is all at the origin. This is when you're looking at from very far distance, all this looks like a point, right? So as far as the whole charge distribution is concerned, it's just 1 over r potential. So that's your 1 over r potential that's showing up, which is what statics would have told you. And you would have told in statics that this is just charge q. Integration over the charge is just charge q. But now this is not evaluated at time t. There is a r prime sitting inside. So there is this is not clean in that sense. And that's what will contribute. But if it was just this piece, again, remember that that's statics. And we know that electric field associated with this is 1 over r squared. And 1 over r squared dies off at infinity. It easily dies off. If you were to use Gauss's law and say that there are no charges at infinity, then that doesn't contribute at all. So this term, if I were to calculate the electric field out of it, it will not contribute. And we will see that this is going to be a higher order contribution. So let's see. So that's your electric potential associated with radiation. And we also introduced the idea of retarded time. So this time that, so in place of t, there is this whole expression here. So which is what we called it the retarded time. So t minus r over c plus r hat dotted with vector r prime over c. That was your retarded time. And if I want to calculate the electric field, I'll take the gradient of this quantity and of course the time derivative of a, and I have to actually hit those r's also. So that involves gradient of t of r, which we calculated last time. So it hits this r here or this r hat here, and we showed that this is r hat over C. It's a gradient of T or simply minus R hat over C. And there is one more piece, which is R hat crossed with R hat crossed with R prime over R. That's 1 over C. Is that correct? Time divided by distance. So distance by time. Yeah, so that's correct. And we will see that this is just for completeness. I have written this. It will come out to be a contributing higher order contributions also. So that's your scalar potential. Just for completeness, let me write the vector potential also. So vector potential A is equal to mu naught over 4 pi. And same idea, this is 1 over R shows up here. And this is d cubed R prime. And instead of the current density being evaluated at normal time, you would say it is evaluated at retarded time. And again, I want to insist that if it was just this main piece that was there, and if there were no these dependencies, then it is a usual static scenario. But we are actually interested in the contribution from the retarded time. So that's the main goal. Okay, so how does this contribute at large distances? So at very large, or in general, we have electric field is equal to negative gradient of the scalar potential and the time derivative of the vector potential, and the magnetic field is the curl of the vector potential. So let me calculate the gradient first. So the gradient of the scalar potential will be equal. Let me explicitly write this. So there's a gradient of 1 over 4 pi epsilon r, 1 over r d cubed r prime, charge density r prime t minus r over c plus r prime c. This is a derivative with respect to position r, not r prime. So where will it hit? So let me box the quantities where it will hit. It will hit this, which is a usual static scenario. This will give you 1 over r squared. It will also hit here. That's your second piece that will hit. And it will also hit here. Or you can also say that this whole thing is actually T of R, and the gradient of T of R is what will contribute, correct? Which we have already calculated, so that helps. Okay. When it hits the first piece, that's an easy one. That's 1 over 4 pi epsilon naught, and that is minus 1 over r squared, and there's our hat, right? So that's your electric field, standard electric field. So this is r hat over r squared. That would have been your electric field multiplied by some charge, right? The negative sign is there because electric field is negative of this. So let me put the negative sign there. So this is positive. Right. So that's your electric field multiplied by, so that's your first derivative. So that's d cubed r prime T of R. But I can hit this T of R also, right? There's another piece there. And let me do that. So that's plus 1 over 4 pi epsilon naught, or 1 over R. And gradient has to go through. This is d cube R prime. It's a R prime integral. So that's gradient of charge density R prime of T of R. Okay. Notice already you can see that I'm not going to keep anything R square dependent. Like at infinity, I don't want any R square dependence. I'm interested in something more stronger than 1 over R square. So I'm interested in the 1 over R potential. I'm going to drop this. So this is of order 1 over R square. So drop. So we're going to keep only 1 over R term. So if we have to get 1 over R, so we already have this 1 over R. So this should not give any 1 over R. Yes. So let's see how do we proceed. So we're going to drop this. So this is equal to what's still in the, yeah. So that's equal to 1 over 4 pi epsilon naught, 1 over R d cube R prime. That is a T of R here. How do I do this? I have a chain rule, right? T of R is not straightforward time, it's a function. So I use chain rule. So I do gradient. So or maybe do it the other way, right? So first take the time derivative. So pretend as if this was time derivative of prime of this t, let's say this is d by dt of this T of R, and then you do the chain rule, right? So first you hit the argument and then you take the derivative. Or better, right? I think it's best written this way. So this is gradient of T of R. Think of it as partial derivative, which is d by dtr of R prime with the argument and then the derivative of the argument itself. The gradient of the retarded time we already calculated, but notice the second term in that had a extra R dependence over the first term. Let me show that. So here, there is a 1 over R dependence here, but there is no such 1 over R dependence here. So this is a stronger dependence at large R compared to this. So X is already a 1 over R contribution from phi. This plus this will make it a 1 over R square. So if we keep track of that, we have to worry about only one piece contribution from here, and that's going to be, so this is equal to minus R hat over C, because the next one is a higher order contribution. Plus, if you want, this is plus 1 over R, order 1 over R. But this order 1 over R plus 1 over R is 1 over R square. I don't want to keep that. This quantity is independent of R prime, comes out. So that's equal to minus is it minus?
I think the gradient of the retarded time has a minus in the second, but we dropped that. Yeah, the second term there, because the gradient on the first term canceled the negative, but you should have still had a negative.
Thank you. So let me put the negative sign right in the front. Thank you. That's a negative sign because I introduced the negative sign later, but then I forgot about it. So that negative sign and this negative sign cancels out. So that's good. So that's what I expected. Get 1 over 4 pi epsilon naught. And then there is r hat over r. Notice we're talking about a contribution to the electric field. It's not 1 over r squared, it is 1 over r. That's the signature of radiation fields, that it will be 1 over r at infinity. And there is, of course, this, oh, I should put a negative sign here again. Yeah, so that's the negative sign. And that's your negative sign, negative cancel, so it becomes a plus. Good. So this is d cubed r prime, and there is 1 over c times this quantity here. I will write it as this is okay the way it is written, but just to make this clear that this is not a normal time. This is we are saying r prime t prime some type prime dummy variable, but I'll evaluate this t prime at t of r, where t of r itself is t t minus r over c plus r hat divided with r prime over c, right, in the leading. And this is 1 over r dependent quantity, and there we have drawn everything else. Okay, so that's your scalar gradient of the scalar potential. I can do the same thing for the curl also, curl of the vector potential. But since electric field has the derivative with A, so let me first do the A by dt. When I do the time derivative, it is kind of clear what is happening. So it is equal to minus mu naught over 4 pi. So the time derivative appears only at one place inside that current density. So that's 1 over r and d cube r prime dy dt. So dy dt of j r prime which can be written as, so this is t of r, right, t minus r over c plus r hat dotted with r prime over c. But this can be also written as, this is the same quantity as this, right? If I had written it as a derivative with t prime, then that's exactly the same, but then you are evaluating it at t minus 2. So, so maybe I should write that down. So this is equal to minus mu naught over 4 pi 1 over r d cube r prime. Sort of trivial statement here, so but still there is no confusion. Thus t prime is equal to t of r. Curl of A goes through similarly as your phi, except that now here, so there is a, like this operation is exactly the same. Instead of this vector coming in and take this, there will be a curl of that quantity that shows up. So this will be equal to mu naught over 4 pi. Oh, I should have a negative sign, I suppose, because this was a negative gradient. This is just a simple curl in there. So this will be negative of r hat crossed with r crossed with j. Only slight, which is not completely algebraic, is this quantity when I'm replacing the time derivatives with this substitutional variables. Okay, let me make sure this is all right. Yes, okay. Okay, good. So we pretty much, so this is your magnetic field then, correct? So this is your magnetic field, and we will write it as R crossed some expression just so that we can call that later on. So let me put this all together. So what we have is a magnetic field, and it's equal, just because it is del cross A, is equal to R hat crossed with a vector which is equal to minus mu naught over 4 pi 1 over r, and that is d cubed r prime, and I will be able to evaluate this. So this is acting like the source. We already see this. This is t is equal to t of r, the retarded time. So what is the source of a magnetic field at infinity, or a radiation field, is not just the current, it is the rate at which current is changing. And you have to evaluate at retarded time. The evaluation at retarded time is because it is so far away, so that takes care of this. But notice this is, if not for any time derivative, remember acceleration, right? Already current is proportional to velocity. So the time derivative of current will have this acceleration of the charge. So that's where the acceleration starts showing up, and that contributes to the magnetic field as a 1 over r contribution. Not 1 over r square. It is more powerful than the static fields. Okay, so what about the electric field? And before that, actually, I should change this a little bit. So there is this mu naught. Maybe I can change this. Remember, mu naught is times epsilon naught is 1 over c square. So mu naught can be written as 1 over epsilon naught times 1 over c square. So I'll take, so there is 1 over epsilon naught and c square I can write here. I'll keep one of the c's with t prime, and the other c I will take it to the b there. So this is c. So remove your, write it as epsilon naught, and then write this as 1 over c. That's just to keep it, which is more convenient for dimensional reasons later on, but nothing non-trivial there. Okay, so what about the electric field? Notice electric field and velocity times magnetic field have the same dimensions, right? Because Lorentz force is q times electric field plus q times v cross b. So the moment I put a c there, they have the same dimensions. Okay, so that's equal to electric field had a contribution of the kind So this was 1 over 4 pi epsilon naught. That was the r hat over r, not r squared, or r, insisting on that. So this is dq r prime. And there is a contribution, two contributions. So one is exactly very similar, 1 over c, but this is r hat and this is r hat crossed. Right? So this is d by dt prime, this is rho, charge density. R prime, t prime, evaluated at t equal to t prime equal to t r. And there is an extra piece also coming in, which is, let me, is there space to write that? Let me write that in a second. That's minus minus mu naught over 4 pi times 1 over r and dq r prime, and that is j of r prime, comma t prime is equal to t4. Right, we want to combine these two, so that's the remaining goal. Our magnetic field has come out. That's exactly the radiation field of contributing to the magnetic field, but electric field is not completely in the form we want, so we want to process this a little. First of all, replace this mu naught with epsilon naught that we did earlier. There's 1 over epsilon naught and a c square. There's 1 over c there, and there is an extra c floating around, which will get consumed in the, after the details we perform. Okay. So to process this, we need to go and think about the current conservation equation. So notice our current conservation equation is d by dt charge density plus the gradient, or sorry, the divergence of the current density is equal to 0. That's our charge conservation equation. And the hope is that we can actually process this to rewrite it in such a way that these two can be combined together. So we are going to, for that purpose, first of all, make this all t prime. Make this all t prime and r prime. So this is all just so that we can compare it with what we have above. So it's nothing special in there. So if we were evaluating d by dt prime and r prime, t prime, and then evaluate it at t equal to t prime, t equal to t of r, right? T prime equal to t of r. So I evaluate this on the left hand side. I do the same thing on the next term, right? So it's negative gradient prime dotted with j of r prime dotted with t prime and t prime is equal to t prime. Notice now the way I'm going to perform this. Oh, am I in the code space? Yes. If I take the gradient operator at this stage, it is hitting only the r prime here. But remember, t of r also has a r prime. So this is t minus r over c plus r hat dotted with r prime over c. Within the code space, yeah. So there is this r prime here. But in this way of operation, this is appearing after it hits this. So this is going to hit here. It does not hit T prime, and then it gets replaced in there. But if I were to do the following, so I simply do L prime dotted with J of R prime, and then T of R. That's not the same as this, because now it will, del prime will hit here, and it will also hit the R prime that's sitting inside this, that's down there. So that's not the same, but I want to write it that way. So that means I made a mistake, so I have to correct that. So I have to add on whatever is the contribution coming from that. So I will say, so I have to add because it is already a minus term, so I will add on to that. So it's a time derivative, T prime, or T of R, right? So T of R, J of R prime, T of R, and hit T of R. Now that's dotted. So that's the correction that. But this is our hat in our way of seeing this. So this is negative gradient prime dotted with J prime. This is minus R hat over C dotted with d by dt prime. Let me write this again as R prime T prime evaluated at T's prime is equal to T of R. Okay. Once we have it in this form, the whole idea, remember, is to simplify our electric field expression. So I will go ahead and integrate this because that's what appears in the first term of the electric field. So I'm going to integrate on the left hand side. This is d cubed R prime T prime is equal to T of R. That's what I want to evaluate. And that's equal to negative of d cubed R prime gradient prime dotted with J R prime T of R. And eventually we are integrating over R prime, so this can come out. So that's minus R hat over C dotted with d cubed R prime and this is, let me also put a 1 over C in front, just so that we get it ready-made there. That's 1 over C, and this is 1 over C time derivative of J okay. This is a total divergence and you're integrating on that. So using Gauss's law or divergence theorem, this will contribute at the boundary, and this will be equal to 0 if J is equal to 0 at boundary. And at boundary, we mean at infinity, right? We are actually very far away observing. Wherever we are observing, if there are no charges, then that will not contribute. And remember, we are talking about this is the sources and the observation is very far away. So wherever the observer is there, you don't want any sources. So that's equal to 0. And then you get a connection between these two quantities. And that's what we want to use for simplifying our expression for electric field. And I want to see the check the sign there. Oh, where is it? Plus. Because gradient of T of R oh yeah, mistake. Notice that this is not grade. So is this visible? Yeah. This is not, this was gradient with respect to prime. So this is a gradient with respect to prime. And gradient with respect to prime is not the same as gradient with respect to the normal variable. And that, remember, is a gradient prime. Where should I do that? Maybe go to the new port space. So gradient of T of retarded time is gradient of T minus R over C plus R hat dotted with R prime over C. And the leading term was this, right? So this hits here and this hits here. So you got minus R hat over C, and there was plus 1 over R, right? Order 1 over R. That's what we got earlier. But that's not what we are interested in. We are interested in gradient prime over of the retarded time. And gradient prime does not care for R. It actually hits this R prime. This will hit all the way here. And how will it hit that? So these two are 0, that's constant. So I changed this direction. So this is still prime, vector R prime, dotted with R hat over C. And that's equal to the dyadic one. Oops. Yeah. If that's 1, so that's equal to R hat over C. So notice the slight difference. This is when it hits when the gradient hits the retarded time, it's minus. When it's gradient prime hitting, it is plus R hat. And that changes the sign appearing in the earlier expression. And I want to fix that. So this should be plus then. So this should be plus. So check this. So I fixed that to plus. And this will be plus. Okay. My bad. Okay. So if you guys allow me, I will need maybe 10 minutes extra today so that I can finish this off. Okay, so we have, yes, thank you. Yeah, is that what you guys said? Yeah, it's fine. Yeah.
Yeah.
Yeah, thanks, Gordon. Yeah. Okay, so electric field then is equal to 1 over 4 pi epsilon naught. We have R hat over R, and that whole charge density integral, I can replace it in terms of integral over time derivative of the current density. And that looks.
Yeah. Camera with you. Sorry.
Oh, the camera. Carried away. Yeah. Okay. Thank you. So the electric field expression. So I'm going to replace this with the derivation we just now did, and that's d cube r prime, and that is 1 over c. 1 over c, and this is d by dt prime j r prime t prime t is equal to t of r. That's the first term, and the second term is, keep it as the old one, 4 pi epsilon naught. Yeah. So this is 1 over r, keep it as it is, and that is 1 over c, and that is d cube r prime 1 over c. Hope I captured everything. This is the same expression that shows up in the magnetic field scenario. So let me call this whole thing K. So let me call this whole thing K, vector K, just temporarily. Sometimes I'll use it again also, so let's just temporarily call this vector K. Why I do that is that whole thing appears there also, and this is r hat dotted with K minus of K. And there is a simplification in that. Okay, and what is that? Because this can be written as r hat dotted with r hat. And then this should be slightly more revealing. That's a vector product, cross product identity. And that is r hat crossed with r hat crossed with K. Check. Yes. Okay. So, but this is nothing but magnetic field itself. So what we have actually shown is that this is nothing but r hat crossed with c times magnetic field. So so what is our radiation field? So the summary here is that, so the summary is radiation fields for our purposes will be electric and magnetic field is, there is an, first let's talk about magnetic field. At very far away region, there is a 1 over r contribution, and it is r hat crossed with, so I'll draw that, so maybe have this K also separated, right? So this is K, if you want. And K itself is, where is my, K itself is dependent on the source. So this is equal to minus 1 over 4 pi epsilon naught, 1 over r, and this is a contribution from the time derivative of your J. at the retarded time. And the electric field is equal to R crossed with C times B. Let's just have a small figure elaborating this. So we have, notice that there is this contributions. So there's all the R primes are in here. All the sources are down there. And it is really small and in a very far away region. In fact, think of this as practically infinity. So you can talk about a dome there. So this contribution leads to, due to some contribution in J, there is a contribution K here. So there is a direction associated with the rate at which J is changing, and that's your K. Irrespective of what K is, R cross K, R crossed with K gives you the magnetic field. So R crossed with K, wherever you are, let's put K in the plane of the paper, R in the plane of the paper. This is a sphere, remember, and your B comes out of this board. It is R and B is perpendicular to that. Cross the R hat again with B, and you get the electric field, which is in this direction. So that's in B. So electric and magnetic field in this way of construction will always be perpendicular to the radial vector R hat. And that's the same thing that happens with monochromatic wave, right? Whenever you talk about electromagnetic waves in introductory physics courses, you notice that, oh, electric and magnetic field are always perpendicular to the direction of propagation. And they are radiation fields. So we are talking about electromagnetic waves now, and at very far away regions, these waves always are perpendicular to each other. They have to be. Like not every configuration of electric and magnetic field has to be perpendicular, but radiation fields are always perpendicular. So B dotted with E is 0 for radiation, always. We'll talk about more. So notice this is 1 over R, this is 1 over R. If I were to either square one of them or take a cross of them or take a dot, they will always have 1 over R squared. And remember, flux goes as 1 over R squared. So energy and momentum, they will all be finite, actually. They will contribute at infinity. So that will be the idea, and we will talk about those next time. So at this point, I will stop here. Thanks for allowing me extra time.
Thanks.
Okay, bye.
Have a good day.
Yeah, you too, Puran.
Thank you.